And we can begin then with Keynote Lecture 3. Is our chair? He needs to unmute himself.
So are we done?
Yes, we're just waiting for Alberto. Can you unmute yourself, please?
Yes, I did.
Thank you. You can begin now.
Should we now? Okay.
Yes.
So welcome, everybody. I'm Alberto Guadagnini, and tonight I have the pleasure and the privilege to introduce our keynote speaker, Dr. Qinjun Kang. A few words of introduction. Qinjun is a senior scientist in the Earth and Environmental Sciences Division at the Los Alamos National Laboratory in New Mexico. He joined LANL as a graduate research assistant in 2001, was then selected as director's postdoctoral fellow after receiving a PhD in mechanical engineering from the Johns Hopkins University in 2004, and became staff scientist in 2005. His current research focuses on modeling and simulation of flow and transport in porous media at the Pore-Scale, multi-scale models, settings across different scales. Applications of his works have comprised a wide range of problems in energy environment, including, amongst others, geological storage of CO2, nuclear waste, hydrocarbon exploration and production, as well as engineered energy storage and conversion devices. Well, I know and I realize that you're not here to listen to me, and so we'll be more than happy now to leave the floor to Qinjun, who will entertain us with his talk about Pore-Scale direct numerical simulations of flow and transport in energy and environment. Qinjun, it's a pleasure to introduce you. Please, the floor is yours.
Okay. Can you hear me?
Yes, we can hear you and we can see your slides.
Okay, great. Thank you, Professor Guadagnini, for the introduction. Hello, everyone. Thank you for being here. It is my great honor to give this presentation. I thank the program committee for this opportunity. Today, I will be talking about the Pore-Scale direct numerical simulation of flow and transport in porous media. I would like to thank my collaborators. Some of them are current or former students or postdocs. Others are LANL or external researchers. I would also like to acknowledge LANL's LDRD program office and the DOE fossil energy program for providing funding support, and LANL's institutional computing program for providing computational resources. Cannot turn the slides. Sorry, probably I need to. Somehow cannot turn the slides. Okay. Maybe try this again. Okay.
We see the second slide. Thank you.
Perfect.
Okay, great. Thanks. This is a, let me get the pointer. So this is outline of my talk. After a brief introduction, I will give 5 simulation examples and then draw some conclusion. Flow and transport processes in porous media are pervasive in energy and the environment. Here are just a few examples in geological systems, including development of petroleum and geothermal reservoirs, geological storage of carbon dioxide and nuclear waste, and the freight and transport of underground contaminants. Here are a few examples in engineered energy systems, such as hydrogen polymer electrolyte fuel cells, flow batteries, microreactors. During operation of these energy devices, there are coupled fluid flow, mass transfer, and electrochemical reactions in some components of these devices, which are porous media. So a better understanding of flow and transport processes is critical for managing improved production of Earth's energy resources, safe disposal of energy-related wastes, and improved performance and durability of engineered energy systems. This problem is very challenging because it involves multiple coupled processes interacting with complex morphology of natural and man-made porous media over multiple lengths and time scales. As an example, the figure on the right is a schematic of hydraulic fracturing for shale gas production. Processes include desorption at the nanoscale, all the way up to hydrocarbon flow from microscopic fractures to production wells, spanning 12 orders of magnitude, the length scale. Experiments have been important to study flow and transport in porous media. However, experimental observations or measurements are often expensive, time-consuming, and sometimes even impossible due to various limitations, such as high pressure, high temperature conditions. So numerical modeling can be a powerful tool complementing experiments. There are two types of numerical models for flow and transport in porous media. Continuum models depend on averaging system properties and governing equations over a representative elementary volume containing many pores and solid grains. Because of the value averaging, the governing equations are not closed, so continuum models depend on empirical relationships such as permeability, porosity relationship. Also, because of the averaging, continuum models cannot capture pore level phenomena or morphological effects, but they are computationally efficient. In fact, most of the mainstream reservoir simulators are based on continuum models. Pore-Scale models fully resolve pore structures and directly solve governing equations at the pore scale. However, the high resolution required to fully resolve pore structure combined with the large scale of interest makes pore-scale models very computationally expensive. Nevertheless, pore-scale models are being increasingly utilized due to rapid development in X-ray tomographic imaging techniques that provide detailed pore structures for numerical simulations, and rapid development in supercomputer architectures that enable pore-scale simulation of rather larger systems, sometimes allowing direct comparison between pore-scale simulations and experiments. Next, I'll talk about workflow and the roles of pore-scale modeling. First, the pore structures of different porous media, such as tight sandstone, carbon fiber, metal form, and aerogel, need to be obtained using some type of imaging techniques, such as SEM. The pore structures are then digitized, which can be directly used in some pore-scale models, such as the Boltzmann model. For some other models, a mesh needs to be generated. Then, based on the flow and transfer processes under consideration, corresponding governing equations are solved numerically. For example, for single-phase flow, the continuity and the Navier-Stokes equations need to be solved. For reactive transport in a single fluid phase, the advection diffusion reaction equation needs to be solved. For ion transport, the Nernst-Planck equation. For electric potential, the Poisson equation, etc. There are different numerical methods to solve these equations, such as Boltzmann method, finite volume, finite difference, finite element methods, as well as smooth particle hydrodynamics. Since these pore-scale models either directly solve the governing equations on a mesh derived from the pore structures, or a kinetic model that recovers these governing equations, they are all called pore-scale direct numerical simulation methods. The simulation results provide detailed information on pore-scale processes, including velocity field, distribution of density, concentration, fluid phase, etc., as well as their evolution with time. The detailed information can then be used to reveal fundamental physics, provide physics-based constitutive relationships, optimize structures, and bridge different scales. The first simulation example is the supercritical CO2 brine two-phase flow. We focus on the effects of inertial force. We know that to correctly simulate a physics system, we need to match the dimensionless numbers between physical and model systems. For multiphase flow, important dimensionless numbers include contact angle, viscosity ratio, density ratio, which are related to material properties, and also capillary number, Reynolds number, which are related to both material properties and the flow conditions. Because these dimensionless parameters control the system behaviors, there are many studies investigating their effects. However, in most of these studies, Reynolds number is not matched. The reason is that it is very challenging to match both capillary number and the Reynolds number. We can say matching both numbers means matching the anisotropy number. As we can say, a small anisotropy number means either a small viscosity to surface tension ratio, which may lead to numerical instability for many numerical models, or a large characteristic length, which means high resolution or fine grid, and hence high computational cost. So in practice, a much lower Reynolds number is often used, which means the inertial force is negligible compared to the viscous force. This may sound reasonable, as the Reynolds number based on the averaged bulk velocity is really not high for flow in porous media. However, recent studies have shown that the inertial effects in supercritical CO2 brine system are not negligible, as the local Reynolds number can be much higher than the bulk Reynolds number. One example is the so-called Heinz jumps, the sudden jumps of the fluid interface accompanied by fluid redistribution and the transient pressure response. It is also found that the time scales of Heinz jumps are independent of the injection velocity and depend only on the fluid properties. Therefore, to correctly simulate multiphase flow physics, it is necessary to match both the capillary number and the Reynolds number. This requires an advanced multiphase model enabling an accurate modeling for small viscosity to surface tension ratio, as well as a highly optimized code for model supercomputers, rendering high resolution simulations of real rock systems affordable. So we have developed such a state-of-the-art Pore-Scale DNS approach based on the Boltzmann method. My co-author Yuchen will present the detail of this model in Pore-Scale modeling session. Here I will focus on some of the results. This slide shows simulations of micromodel experiments of liquid CO2 displacing water. We performed two simulations, one with both the capillary and Reynolds numbers matched with those in the experiment, and the other with only capillary number matched and with a smaller Reynolds number. We can say this simulation with smaller Reynolds number predicted less flow pathways. For example, the secondary flow pathway marked by the white ellipse observed in the experiment is not produced by this simulation. As a result, this simulation underestimates the final CO2 saturation. But the simulation with both capillary and Reynolds number matched with those in experiment correctly predict both displacement patterns and the final CO2 saturation. We have also simulated the co-flooding experiments of supercritical CO2 displacing water. These are high-resolution microcity images of a Bentheimer sandstone. We reconstructed the pore structures from these images and cropped a subset to reduce computational cost. We performed 6 simulations with a combination of 2 capillary number and 3 Reynolds numbers, or anisotropy numbers. This is the animation of one of the cases. CO2 is in white and water in blue. The figure on the right shows saturation profiles along the flow direction as the breakthrough point for 3 cases with the same capillary number but different anisotropy numbers or Reynolds numbers. we can say that the saturation increases with the inertial force or Reynolds number, or as a decrease of, with the decrease of anisotropy number. This slide shows supercritical CO2 saturation as a function of injected volume for all 6 cases. We can see stronger inertial effects result in higher saturation, consistent with micromodel experiments. This conclusion holds for both capillary numbers, which means that the inertial effects do not depend on injecting velocity, consistent with Heinz jumps, just mentioned earlier. Next, I'll talk about the reactive transport during solubility trapping of carbon dioxide. As shown in this figure on the right, solubility trapping is one of the 4 mechanisms to trap CO2 in a geological formation. It is also required for mineral trapping. It involves dissolution of supercritical CO2 into brine at the supercritical CO2 brine interface. Related chemical reactions can be described by the following equations in the kinetic form. It is challenging for both experiments and the numerical simulations to capture these processes at the Pore-Scale because it involves multiple coupled dynamic processes such as evolution of fluid-fluid interfaces, chemical reactions in the bulk solution, and at the phase interface, and multi-component mass transport in the solution. Current Pore-Scale studies focus on either immiscible supercritical CO2 and brine two-phase flow, as I just shown, or reactive transport involved in single-phase CO2 saturated brine. We have developed a multiphase multi-component reactive transport and exposure model to simulate this problem at the Pore-Scale. The figures on the right show time evolution of supercritical CO2 saturation or averaged concentration of dissolved CO2 for 4 different initial supercritical CO2 saturations. The figures on the left show the evolution of supercritical CO2 phase distribution and the concentration of dissolved CO2 for 2 of the 4 cases. For lower initial supercritical CO2 saturations, CO2 are completely dissolved, while there is supercritical CO2 phase for higher initial supercritical CO2 saturations. We can say dissolution of supercritical CO2 is highly heterogeneous, depending on local pore structures and multiphase distributions. Also, we can see a constant average concentration does not indicate equilibrium at the Pore-Scale. For example, at time 1,000 seconds, for this case, the average concentration is almost constant, but there is still a small CO2 droplet in the pore space, which is dissolving. These figures show the specific interfacial area as a function of time for supercritical CO2 saturation. As a function of time or supercritical CO2 saturation. We can see while the specific interfacial area differs significantly for different initial supercritical CO2 saturations, an linear relationship on log scale between specific interfacial area and the supercritical CO2 saturation is obtained for all the cases. Of course, we see 2 slopes here. A linear relationship has been found for immiscible fluids in literature, but there are no change in slope. Here, we speculate that the 2 slopes were caused by dissolution of CO2 into water at the interface, but this still needs to be confirmed by experiments. Interfacial area is important quantity for multiphase flow. It should play an even more important role when interfacial chemical reactions are considered. So we have shown that Pore-Scale simulations can quantitatively determine the interfacial area and hence can provide constitutive relationships required in continuum models. The next example is oil-water in mixed wet porous media. We focus on the effect of wettability heterogeneity. The surface wettability in examples shown so far is uniform, but in reality, porous media are often non-uniformly fractionally wet. For example, because different minerals have different surface weathability properties, the mineralogy heterogeneity in geological media can introduce weathability heterogeneity. Also, the adsorption of organic species can introduce fractional weathability. To decouple the weathability heterogeneity from the pore structure with heterogeneity, we use a simple pore structure of packed circles in a two-dimensional domain in this study. The surface of the solid circles can be either oil wet or water wet. From A to F, the fraction of the oil wet solids increases from 0 to 1. Here is some information about the pore structure, and this table lists the properties of fluids used in our simulations. This figure shows relative permeability of water in various fractionally wet porous media. We can see the water's relative permeability in purely oil wet porous media, marked in red, is higher than that in purely water wet porous media, marked in black. At high water saturations here, the water relative permeability increases with the oil wet solid fraction, you can see. But at moderate water saturations, the water relative permeability in fractionally wet porous media. So the cases, all the other cases except for black and red. So that can be even lower than that in the purely water wet porous media, indicating additional flow resistance in mixed wet porous media. We also plotted the sum of water and oil relative permeability as a function of water saturation. This sum can be an indicator of flowability of the two-phase fluid. So we can say at low or high water saturations, the flowability in fractionally wet porous media is between those in purely water wet porous media and purely oil wet porous media. At moderate water saturations, however, the flowability in fractionally wet porous media becomes the lowest. So we suspect the additional flow resistance results from Pore-Scale fluid distributions, as shown in the figures on the right. Compared with the purely oil wet porous media or water wet porous media, the phase distribution in the mixed wet porous media is more scattered, leading to more oil-water interfaces, and hence stronger capillary effect and additional flow resistance. Now I'll switch gears and talk about carbon mass transport and chemical reaction in energy systems. It is known that significant losses in energy devices are related to mass and charge transport, and numerical modeling can be an efficient tool to optimize microstructures for improved performance and reduced cost for energy systems. Because of the limited time and the diverse audience, I will not go into detail of any energy devices. Rather, I will show some results obtained using very simple pore structures and generic reaction kinetics. Interested audience can refer to our relevant publications or attend the session of electrochemical processes in porous media, in which some of my collaborators will present. This simulation example is reactive transport in a post-it microreactor, where the ammonia decomposition takes place to generate hydrogen as the post surface coated with this expensive catalyst. Fluid flow, heat transfer, transport of reactant and products, chemical reactions are all considered in our simulation. We can see for the same number of posts, which means same amount of catalyst, the conversion efficiency for the top arrangement is twice that from the bottom arrangement. This is surprising, as a simple rearrangement can make such a big difference in conversion efficiency for hydrogen production due to improved flow field and reactant distribution. We have also studied effects of macropores in hierarchical porous media. The original pore structure was derived from a heterogeneous micromodel we make the pore structure hierarchic by adding uniform empty squares. We also vary the size of the squares. As the size increases, so does the porosity. A reactant is introduced at the left inlet and diffuses into the system and is consumed at the solid surface through a first-order reaction. The figures on the left also show the reactant distribution for the case without macropores and the case with macropores. All the other conditions are the same. We can see visually that the reactant penetrates further into the domain with macropores. The figure on the right shows the distribution of vertically averaged reactant concentration along X direction. We can see as the porosity or the pore size increases, penetration length of the reactant increases. This demonstrates that macropores can enhance the mass transport. This probably is kind of intuitive. These figures shows average reaction rate on the solid surface as a function of reaction rate constant for different pore structures. At a very small reaction rate constant, mass transport is fast compared to reaction. Thus, the average reaction rate for different pore structures is almost the same. In this case, adding macropores has minimal effect. As reaction rate constant increases, chemical reaction becomes faster and mass transport becomes the limiting factor. In this case, introducing macropores enhances mass transport and hence increases the average reaction rate. The effect of macropores on total reaction rate is more complex and less intuitive. It decreases with porosity at low reaction rate constant, but it increases with porosity at high reaction rate constant. At a moderate rate constant, it first increases and then decreases. The reason is that macropores have two opposite effects. Number one, enhancing mass transport, and number two, reducing total surface area. At the low reaction rate constant, the process is reaction controlled. The effect of reducing total surface area outweighs that of enhancing mass transport. Therefore, the original porous media without macropores performs the best. As the reaction rate constant increases, the opposite occurs. Note, larger pores or smaller surface area also means less catalyst is needed. We have also studied the effects of the distribution of macropores by considering structures where the size of the macropores gradually changes along the transport direction. So in A, the size of the macropores or open squares gradually increases from left to right, resulting in a front tight, back loose structure. Conversely, the structure in B is front loose, back tight, and C shows uniform distribution of the same size macropores. The porosity of the three structures is the same. The three figures on the left also show the distribution of the reactant concentration for the three structures. The figure on the right shows the distribution of vertically averaged reactant concentration along X direction. We can see the front loose, back tight configuration is best for enhancing reactant transport, followed by the uniform distribution, and then by the front tight, back loose arrangement. So we have shown that hierarchical porous media with a combination of pores of different sizes and distributions can provide optimal balance between surface area and mass transport. However, for Pore-Scale models to become a useful tool to optimize the microstructures of porous media for better performance, the computational efficiency of these models need to be significantly improved. This is made possible by machine learning. So we have developed a machine learning workflow for fast prediction of transport properties of porous media. First, we generate a large number of pore structures. Then we perform Pore-Scale simulations of relevant transport processes and predict the transport properties of interest. The generated large dataset is then used to train a machine learning model. Once successfully trained, the machine learning emulator is then applied to other pore structures to simulate the same transport processes and to predict the corresponding transport properties. The machine learning emulator will have comparable accuracy or acceptable accuracy, but it will be orders of magnitude faster than the Pore-Scale simulation. This is the first example of our workflow. This is the architecture of our machine learning model. And this figure is a comparison between the trained machine learning emulator and the Boltzmann model for predicting effective diffusivity, probably one of the most, the easiest problems here. We can see the agreement is very good, but the machine learning emulator is orders of magnitude faster than that Boltzmann model. We are working on extending this machine learning model to three-dimensional space and to other properties. Ultimately, we would like to develop the workflow to optimize this structure, control processes, and then improve performance of porous media. So the final example is scale bridging simulation of shale gas using combined machine learning, molecular simulation, and Pore-Scale modeling. Many pores in shale formation are in nanometers. Hydrocarbon in these nanopores behave differently than in the bulk. To accurately predict hydrocarbon storage and production from shale, nanoconfinement effects such as adsorption and slip flow must be considered. However, such fine-scale modeling requires molecular simulation, which is very expensive and cannot be applied to real shale samples with many nanopores. On the other hand, Pore-Scale models such as the Boltzmann can handle such complex geometries much easier at a larger scale, but it needs to be informed by molecular simulations to properly account for the nanoconfinement effects. The goal of scale bridging simulation is to use fine-scale MD simulation data to inform Boltzmann simulations. We have built a machine learning surrogate model that captures adsorption effects across a wide range of parameter space and bridges the MD and the LBM scales using a relatively small number of MD calculations. We obtain physical adsorption data from MD and long-informed adsorption data from LBM to construct an MD emulator and an LBM emulator. By matching the density profiles of the emulators, we then construct an upscaler. This upscaler finds the effective parameters. So in this case, just effective density, effective temperature, and adsorption parameter for the LBM informed by the fine scale data. The surrogate model is 7 orders of magnitude faster than the MD simulation. And it is agnostic to the physical system. So we are incorporating other nano-confinement effects into our framework, including slip flow, effective viscosity, equation of state, phase change. We'll also extend our model to complex pore geometries. So here are some conclusions. So I will not read through the list. Rather, here I would like to point out that the Pore-Scale modeling is a fast-growing area, and I'm sure there are other important methods and applications I didn't cover. Here I have only given a brief overview of some of our recent work. I hope it is useful, especially for early career researchers. With that, I'll conclude my presentation. Thank you for your attention. I would like to take any questions.
Well, thank you very much, Qinjun, for the nice and stimulating talk. And I think we can start our Q&A session right now. And I'm not sure I see any questions for the moment on the dashboard, actually. So
I see someone raised their hand during my presentation. So yeah.
Yeah, I texted the person who raised the hand. It was a mistake. So, but that's okay. Anyway, it happens. So can I start asking a couple of questions? The first one is related. There is something that was just not clear, maybe just to me, and it was about the geometry of the microscale systems. You were talking about reactive transport. Did you deal also with precipitation dissolution with changing of the geometry of the space of the pore space, or not yet?
We have work considering all this. I mean, couple the flow, reactive transport, dissolution, and precipitation, and all the solid geometry. But I haven't shown this today. But yeah, due to I only have 30 minutes, so.
And with reference to this part here, what are, in your opinion, the key barriers or areas of development that you already mentioned something in your presentation, but what would you envision as key areas of expansion in pore-scale simulations in terms of processes, for example?
His video stopped. He may have.
Yeah.
Okay, he's back. There are 3 questions under the keynote lecture.
Okay,
1,
I think
2, 3, 4. Okay. Oh.
Yes, you're back.
Okay, sorry, somehow I think my internet has been acting up this morning.
Okay, so what I was asking.
So I don't know how. Okay, go ahead, please. Sorry.
No, what I was asking was, in your view, if you can point out what are the key areas of expansion in pore-scale modeling.
Okay, so far, for example, I haven't considered the solid the deformation or sweating of the solid phase here. So that's or geomechanics.
Well, he's seeming to have some problems with
Yes.
his internet.
And on top of them, for some reason, I do not see the questions in the Q&A panel. If you can see them, do you see them, Christy?
You can try refreshing it. That might, if you have a refresh.
Yeah. No, still don't see them.
Are you in keynote lecture or are you?
I'm in the keynote lecture.
Sure. Okay. I can ask them if you would like me to, but we'll have to wait till our speaker is back.
Qinjun is back. Okay.
Sorry, my internet is. I think the problem is from my side, right? Can you hear me now?
Yes. And
okay. Sorry, a brief answer is like I don't know how much you have heard. We haven't considered like a solid deformation, solid phase. But yeah, we would like to consider that or geomechanical effect. So it would be nice to couple like a micro geomechanics with reactive transport. But that's very challenging. But that's something we are hoping to look into in the future. Or yeah, thank you.
Okay, thank you. Then I can see Tisa who raised his hand. Maybe you can unmute him. Okay. Hi, Tisa. Tisa?
It may not work. It doesn't work for everybody.
Okay, can you hear now?
Yes. Hi, Tisa.
Yes. So, Qinjun, very nice talk and I really enjoyed it. But I have a question related to some of the experimental I had done with supercritical CO2, we found that in the macroscopic models, we can capture the injection phase quite well, but then during the redistribution, we had difficulty matching the traditional macroscopic model. So it seems like these Heinz jumps you talk about, that happens mostly during the redistribution or during the injection phase.
That's it. So I guess maybe both.
Maybe take your video out so we can hear you, because the video you are
Okay.
breaking.
Can you hear me now?
Yes.
Yeah.
Okay.
Take the video. Okay.
Yeah. Thank you, Tisa. I think that's an excellent question. I have to assume it probably happens both, because as I shown earlier, the Heinz jumps, the time scale is independent of the main flow velocity. So even when injection is stopped, it probably will still happen. And also the time scale is kind of independent of the previous process. So I would assume it's maybe not so dependent on which phase you are at, like whether it's injecting or redistribution.
Yeah, so during the injections phase, the Heinz jump effect will be drowned by the pressure driven flow, because this is controlled by capillarity, because push the fluid, then maybe that may not be that significant.
Yeah, I tend to think like a Heinz jump is kind of a material property. It depends on the pore structure and fluid properties. So it's not so sensitive to the pressure gradient at the macroscopic level.
Okay. Thank you.
That's my view. Thank you.
Thank you, Tisa. I can see some questions right now, and one of them is, could you comment on how to couple nanoscale multi-component phase behavior into your model? Some nanofluidics experiments show that EOS with capillary pressure may provide enormous results. So the question is about coupling nanoscale multi-component phase behavior into your model.
Yeah. So we would like to use this framework we just established, because because it's, as I showed, it's agnostic to the physics system. So they don't know the physics, but still they can somehow by matching the MD simulation, by matching some characteristic properties, we can actually develop a surrogate model to extract some information from MD to inform the larger scale model. Of course, we need to have a fundamental understanding of the physics, at least, and incorporate them into the molecular simulations. That's a premise.
Okay, thank you. And another question is actually related to the way machine learning training or machine learning results can be affected by the resolution of the images that you're using. Does it change dramatically?
Absolutely, I think it should. And of course, and the same way like a Pore-Scale modeling also depends on the resolution of the image, right? So at some level, for example, the pore structures probably are not connected. There is no flow. If we perform Pore-Scale simulation on those microstructures, there will be zero probability. But at a finer resolution, properties are connected. Then we have different results. The same thing happens with machine learning. But if we supply the data, the structure and Pore-Scale simulation data to machine learning, ideally, machine learning will produce the same results or similar results as a Pore-Scale modeling.
Thank you. I think we have, I can ask one last question, and it's about the impact of wettability heterogeneity. So so first, you studied the impact of wettability heterogeneity for a given geometry of the pore space. And the question is, do you think you can generalize your results for different Pore-Scale structures? And on top of this, if you don't mind, my understanding was that you used 2 contact angles in the system, right? So oil wet and water wet. So 2 specific values of contact angle. Did you try with the continuous distribution of contact angles?
No, that will be, let's say, very, let's say, sophisticated. In fact, this is just one contact angle. Here, it's just one contact angle, but the surface property is changing. So either it's oil wet or water wet. Yeah.
Got it. And since you worked on a given geometry of the pore space, do you think you can generalize your results for different pore scale structures? Or are they tied to the specific structure that you studied?
I see. For the additional resistance, I think we are kind of confident that it probably can still hold for other geometries. But for the quantitative results, I guess that's probably structure dependent. But as long as the detailed pore structures and the surface properties can be provided, we can perform the simulation. So,
thank you. The very last one, which is related to the number of simulations, at least in your examples, that you needed to train your machine learning model.
Well,
So
you mean how many
simulations did you need?
Okay, so here I think we need for the scale bridging, we run like thousands of MD simulations and thousands of Boltzmann simulations. For the property like effective diffusivity, we run hundreds of simulations. So yeah, I think that this highly depends on the processes or transport properties of interest and how complex the transport processes are. For example, for multiphase flow, there will be probably a different story.
Of course, of course. Well, I think we are right on time. So it's 5 minutes to 7 p.m. here in Milano. And so I think it's time to thank Qinjun for the wonderful talk and the nice opportunity that he gave us to follow his work. So thank you, Qinjun, and thanks everybody for joining us on this wonderful keynote lecture, and enjoy the rest of the conference.
Thank you.
Have a great evening.
Bye-bye.
Thank you.
You too. Bye-bye.